Hello friends, let's start with the first topic of our course on material science and engineering. And as in the introductory lecture also we discussed that you can go from bulk material to a microstructure to atomic structure, and also you can classify them in different crystal systems and crystal structures. So let's start with how the atom is, what is the structure of the atom. Okay, so let's start with atomic structure and bonding, and you will realize in the next slide itself I will show you that for the same type of atoms, bonding itself make huge difference in the properties. Okay, and it goes with the theme as I discussed in the introduction also, that if you change things for the same type of atoms also, okay, for example in this case bonding, there is a huge change in the properties. Okay, so that is the importance of understanding this, that we would like to know what are atomic structure, okay, and they determine the type of bonding which atoms are going to have, and bonding decides the properties of material. Okay, for example, as I told you that carbon, when it is in graphite form, okay, it has a different type of bonding. It has a in the plane it has a covalent bonding, and across the layers it has van der Waals bonding, and it is soft. You can you know that in your pencil you have graphite, and you can easily write and you can easily sharpen the pencil. Okay, so it is a soft material, it is not very hard. But the same carbon atoms, when it has a different type of bonding, okay, in this case covalent bonding with all the carbon atoms, then it is a new form of, or a different allotrope of carbon, which is diamond, and it is hardest material known to man. Okay, so just by changing the bonding between the same type of atoms, okay, we have changed the properties to such an extent. Okay, if you compare now between, let's say, metals and ceramics, okay, two class of materials widely used. Okay, metals have slightly weaker bonding, okay, and their properties are decided by what type of bonding they have, which is called metallic bonding. And ceramics have either ionic or covalent bonding, okay, and their properties are decided because they have this type of bond and what is the bond strength and so on. Okay, so we will see this type of bonding. First we will see the atomic structure, okay, which is basically your 10th class physics or up to 12th class physics. Okay, just a recap of all the ideas which we have already you must have seen at some in some other in 10th or 12th. Okay, so let's start with that. So atomic structure, if you see, okay, an atom consists of nucleus which has proton and neutrons and electrons orbiting around it. Okay, proton is positively charged particle, neutron is neutral, and electron is negatively charged particle. Atomic number is equal to number of protons, and because atom is electrically neutral, okay, the number of protons will be equal to number of electrons. And the charge on of an electron is given here in coulombs. Atomic mass, if you want to understand, then it is basically the atomic mass if you combine all the mass of the proton and neutrons. Okay, we don't consider here electrons because electrons are order of magnitude, the mass is order of magnitude lower than the proton and neutron, and it doesn't affect the overall mass of the atoms if you consider electrons also. Okay, so it makes no sense, and we will only consider protons and neutron for calculating the mass of the atoms. Atomic mass unit you can express in AMU, atomic mass unit, which is 1/12th of atomic mass of the carbon 12. 1 mu per atom is equal to 1 gram per mole, and we also know that 1 mole of a substance contain these many number of atoms. Okay, so for example, if you want to know what is the atomic weight of iron, it is 55.85 AMU per atom or 50.585 gram per mole. Okay, so in 1 mole this many grams of iron will be there, and similarly you can calculate for other elements. It is not a very complicated thing. It is just an example just to brush whatever we have already studied earlier. Atomic models, if you want to see that how this electron, neutron, proton are arranged in an atom. Okay, so one of the early model was given by Niels Bohr, and it is called Bohr model. Okay, and what Bohr model gives is that the electrons are orbiting around a nucleus. A nucleus contains both proton and neutrons. Okay, and this electron orbit in a discrete orbit. Okay, so as you can see, we have shown 3 orbits here, and we have named them as, or they have proposed at that time as KLM. Okay, so these are, according to Bohr model, are very discrete orbits. Okay, with discrete energies. Okay, and the position of electrons, as you can see, are very well defined in these orbits. Okay. However, the electron will be orbiting around in the orbit, but it can change the orbit. Okay, so when it changes the orbit, it will either emit some energy, okay, or absorb some energy during the transition from one orbit to the next orbit. Okay, so this is what is the Bohr model, but it was a very simple model. Okay, and people found out that it is not able to explain some of the experimental evidence, or it is violating some other principles. Okay, for example, it could not explain the spectra of atoms containing more than one electron. So it was only able to give or predict proper results for hydrogen. Okay, any atom which is more complex, which has more number of electrons or protons, it was not able to give the correct predictions. Okay, it also violates the Heisenberg uncertainty principle. Okay, because Bohr model could predict both position and momentum at the same time, which is not possible according to Heisenberg uncertainty principle. Either you can tell the position, okay, or you can tell the momentum. Okay, you cannot tell both quantity for a particle. Okay, to take care of this issue with Bohr model, okay, a new model was proposed which is called wave mechanical model. Okay, in this the electrons are orbiting around the nucleus, not in discrete orbit, but in a cloud. So you can see a diffused ring is shown around the nucleus. Okay, and the electron can have any position in this diffused ring. Okay, and the position is given by some probability function. Okay, so this is the probability of electron in a particular radius away from the nucleus. So this is the distance from nucleus. This is the probability of finding an electron around the nucleus. So wherever the probability is more, you will have more chances of finding electron there, and actually it coincides with the whatever the radius was predicted by Bohr model. Okay, so that way it kind of come very close to what Bohr was saying, but in this case now we have no we cannot tell where the electron is, but we can only give you a probability of a electron at a particular position or at a particular distance from nucleus. The probability is maximum, okay, and that coincide with the Bohr's radius. Okay, so that much is there. Okay, so this is what is a wave mechanical model. Now if we come to the atomic interaction between two atoms, okay, so we have already seen that an electron consists of neutron and proton in a nucleus, and electrons are orbiting around this nucleus. Okay, so when you bring two atoms close to each other, okay, there is bound to be some interaction between all these particles. Okay, already we have seen that proton is positively charged and electrons are negatively charged, and a neutron doesn't have any charge. Okay, so when these two atoms are going to come close to each other, all these negative positive charges are going to interact with each other. Okay, and when you do that, okay, there is going to be some force acting between these different charges or charged particles. Okay, and that is how what is shown here. Okay, so if you see the first graph here, this is force on the y-axis, and you have on the x-axis you have interatomic separation R. Okay, and there are three forces are shown here. Okay, one is attractive force. Okay, that is this is how it is going to change. So if I, let's say I bring two atoms, they are at a very far distance, for example, and it is so far that they are not able to interact with each other. Okay, and now I am bringing this atom closer to each other. Okay, so what will happen? Initially there will be an attraction between the two atoms. Okay, the attraction will increase as a function of distance according to the curve shown here. Okay, the repulsion will be the force of repulsion is shown by the green color here. Okay, and the net force, which is the summation of these two forces, is shown by the this red color curve here. Okay, so you can see that this red color force, which is the summation of the attractive and repulsive force between the atoms, okay, it is crossing this x-axis at a particular location here. Okay, and that position I am calling as R naught. Okay, the R naught means at R naught my force on the two atoms is 0, the resultant force because of this attractive and repulsive force, that is 0. Okay, so my atoms would like to be in minimum discomfort. Okay, you can say that wherever they have minimum force on or where they have 0 force on each other, they would like to be there. Okay, so this is what we call as equilibrium distance between two atoms. That is what they want to have all the time. Okay, why they want to have all the time this 0 force on the each other? Because if you see the second curve now, potential energy, okay, and again the same thing, you have repulsive that how the energy of repulsive energy will be changing, or attractive energy will be changing as a function of separation. Okay, this is the net energy curve is drawn for the two energies. Okay, and where your force is 0, you have the minimum potential energy. Okay, so again from energy concept we always see that any object want to have minimum energy possible under the given circumstances. Okay, so we see that where the force is 0, you have a energy minima also. Okay, so my atoms would like to be at an equilibrium distance here, which is shown by these two atoms here, that they are just touching each other and they are at equilibrium distance. Okay, if you bring them closer to each other as shown here as green, two green atoms, okay, they will repulse each other. Okay, if you take them far apart, which is shown by blue atoms here, okay, then they will experience the attractive force. Okay, why this attractive and repulsive force are there? The attractive force is due to electrostatic attraction between electron and nucleus when you take them far apart. So only the electron and the nucleus are interacting, okay, between one atom and another. Repulsive force is when you bring them very close to each other, now their nucleus start interacting with each other. So suppose I take an atom like that and I take another atom like that. Okay, so these two are nucleus. Okay, so when I bring them closer, now you can see that they are also started a positively charged nucleus is seeing a positively charged nucleus here. So they will repulse each other. Okay, so they don't want to be close to each other. If you take them far apart, the electrons of this atom will be attracted by the nucleus of the other atom. Okay, so these are the two forces which is going to act. At equilibrium separation, net force is 0 and potential energy is minimum, as we just discussed. Okay. So, now there is one term we are bringing here which is called bond energy. Okay. So, the bond energy is the energy which is given by where the minima is there. So, if I measure from this minima up to the 0 energy, okay, this is my E naught, okay, this is the E naught, okay, measurement from x axis to the minima here. So, I can have different energies depending upon the for different materials or different atoms, okay. So, maybe in one case I may have energy like this, okay, and this is what I am calling as E naught, okay. For another material or of another type, another atoms, maybe the energy is something like this, okay. So, now in this case my energy has increased, okay. So, let us see if I draw it here again somewhere here. So, this is now E naught for another material, okay. So, now you can see that for this material the energy is even lower, okay. So, the bond strength of this material will be more than the bond strength of this material, okay, and that is going to affect the properties of the material, okay. So, you can see that if I have higher bond energy E naught, I will have higher melting point, okay. It will be more difficult for me to break the bonds and take it into the liquid phase. I will have higher elastic modulus, okay. I have to apply more force to separate them, okay. So, if I have higher bond energy, I will have higher melting point and higher elastic modulus. Now, atomic bonding can be of different types, okay. In the previous slide we did not talk about what kind of bonds are there, we just talk about that there is going to be some interaction between the nucleus and electrons of two atoms, okay. But the bonds can be of different types, okay. So, there can be, you can classify them into two categories here. One is primary interatomic bonds, which is ionic, covalent and metallic, and secondary bonds, which are van der Waals forces and hydrogen bonds, okay. Now, if we try to understand what do we mean by ionic bonds, okay. The ionic bond means you have two ions which are interacting, okay. So, for example, usually these ionic bonds form between metallic and non-metallic atoms, okay, and metallic atoms give valence electron to the non-metallic atom, okay. So, by giving electron it becomes an ion, okay, and by accepting an electron by non-metallic element it becomes another ion, okay. So, for example, if you see the sodium atom, okay, it has unfilled shell, okay. So, its electron configuration is 2 at 1, okay, 2 electron in the first shell which is K shell, 8 electron in the next shell which is L shell, and then in M shell you have 1 electron, okay. It needs 8 electrons here. Chlorine atom, if you see, it has 2 at 7 electronic configuration, 2 in the first shell, 8 in the next shell, and then the 7 in the third shell, okay. So, if sodium gives 1 electron to chlorine, okay, it will become stable because it will have all the shells as filled. Similarly, chlorine will also get 1 electron to fill the shell of the chlorine atom, okay. So, that is what they will do, okay. It is a mutual beneficial situation for both the atoms, okay. One atom will jump from sodium go to the chlorine. So, now it become Na plus ion because it has given 1 electron, okay. So, now it is a positively charged, 1 extra proton is there now which make it positive. So, it is 2, the electronic configuration is of this ion is 2 8, chlorine has accepted 1 electron, okay. So, now it is negatively charged because the electron there is one more electron than the protons, okay. So, now the electronic configuration is 2 8 8, and because of this positive and negative charge, there will be a Coulombic interaction between the two ions, okay, and that is what bonds them, okay. That is a very good situation for them, okay, giving each other one electron, okay. One electron is transferred from no sodium to chlorine, and then you have some attraction because they are now oppositely charged particles or charged atoms, okay. If we come to the next type of bonding, which is covalent bonds, okay, in this type of bonding atoms share, okay, they do not give permanently one electron, but they share all the time, okay. So it is a sharing kind of relationship between the two atoms, okay. So they share their valence electrons to get a stable configuration formed between atoms of similar electronegativity. Diamond, silicon, germanium also have covalent bonds, okay, and that is what gives them sometimes very high hardness. For example, diamond is a very hard material, okay. So carbon atom has electron configuration of 2 and 4, okay, and hydrogen atom of course has only one electron. It in one of its shell, for the case shell, it needs 2 electron in the case shell. So what it will do, 4 hydrogen atom will combine together, will come together, okay, kind of, and they will arrange like this, and each hydrogen atom will start sharing an electron with the carbon atom, okay, and now hydrogen also has 2 electron, okay, and if you have 4 hydrogen here, the carbon the L shell of the carbon also has 8 electrons, okay. So now it is again a very nice situation for both the atoms, okay. So sharing between carbon atom and 4 hydrogen atom will takes place, and that is what we know as methane, CH4, okay. So this is an example of covalent bond, okay. Now another kind of bonds which are very useful, okay. These are because these form in metallic materials, and that is why they are called metallic bonds, okay. So in this case, actually in metals the electrons are not bound, the outer valence shell electrons, okay, they are not bound with a particular atom, okay, they are free to roam around, okay. So they form a electron cloud around the atoms, okay, and because electron has been removed, there is no particular electron associated with an atom, okay. What we are saying that all these atoms are positively charged ion, okay, and their valence shell electrons are just freely roaming in the whole material, okay. So because of this roaming around and because they are free, actually they also have very high electrical conductivity, okay. And the attraction between the atoms or the bonding between the atoms is because of again the Coulombic attraction between these two oppositely charged species, the electron cloud and the iron core. So you can see understand this electron cloud as a glue, okay. So you have particles, okay, and there is a glue which is in between them, which is an electron cloud, and that glue is holding them, all the these atoms or ions, okay, and giving what we call or what we know as metallic bonds. Now if we come to secondary bonding, okay, the secondary bondings are there are 2 types, okay, van der Waals bonding, or we also know them van der Waals force, and hydrogen bonding, okay. So first let us have a look at the van der Waals bonding, okay. Of course it is weaker in comparison to primary bonds, okay. Primary bonds are much stronger, all the ionic, covalent and metallic bonds, okay. These are weaker in comparison to these primary bonds. The energy is around 10 kilojoule per mole, okay, and this type of bonding, okay, this bonding arises due to the formation of a dipole, okay. What happens is that there is no symmetric distribution of electron around the nucleus, okay. So because of that it gives you a kind of a charge asymmetry here. So you have a positive charge here, negative charge here. Similarly, in another atom also you will have a positive and negative charged portions in the same atom. Okay. So this positive charge and negative charge will interact, again you will have some Coulombic attraction. Okay, attractive forces will be there between these two dipoles. Okay, and of course this is of not very high, the attraction or the charge on this dipole is not very high, so this bonding is also not very strong. Okay. So because of this dipole formation there will be some attraction and there will be a bond between them which will be called as van der Waals bonding. Okay. In fact, in graphite, again I am coming back to the graphite as we discussed in the first slide also. Okay, that the graphite has a structure like this, it is in form of layers. Okay. So if you see in the layer in plane, the carbon atom have covalent bonds, okay, which is we know are very strong. Okay. But between the layers they have van der Waals bond, which again we know are not very strong. Okay. So what happens, the covalent bond which is in the plane, those are strong. If I deform the graphite in plane, if I do any deformation, you will see that it has very high strength. Okay. But if I want to suppose slide one layer over another in graphite, it is very easy because there are van der Waals bonding only, and it is very easy to break them and form new bonds by sliding. Okay, so sliding is very easy in case of graphite because between the layers there is no primary bond, it is only van der Waals bond which are much weaker as compared to the primary bonds. Another type of secondary bond is what we call as hydrogen bonds, and that is what is present in water molecule. Okay. So a water molecule or H2O has a hydrogen bonding between the two molecules of H2O. Okay. So usually you find this type of bonding in molecules where one of the constituent is hydrogen. Okay, and the electrostatic interaction between hydrogen and another atom of high electronegativity gives this kind of bonding. Okay, water molecule is a good example of this bonding between hydrogen of one molecule with oxygen of another molecule, and that is why it is able to bind together, and you can see that water is not easily just separating into molecules. Okay. Now, if I want to summarize all the ideas which we have discussed in this particular lecture, okay, then I can put all this in a nice classification like this, where we have bond type, the strength of these bonds, okay, and how these bond affect the properties. Okay, so for example, first we have ionic or covalent bonds. These type of bonds have very high, the bond strength is very high. Okay, so it is around 450 to 1000 kilojoule per mole, and because they have high bond strength, they also have high melting point. Okay, so you can understand in solid the atoms have this kind of bonds. Okay, when you want to take it into molten condition or in liquid condition, what you have to do, you have to break this bond, then only those atoms in a liquid atoms are can move freely. Okay, they don't have any fixed position, whereas in solid they have fixed positions. Okay, so for them to move freely in the liquid, okay, I need to break this bond. So if the bond strength is high, it will take more energy to break the bonds, that is why the melting point will be higher. Of course, the strength will be higher because you have to first do some kind of stretching. Okay, so elastic modulus will be high, the yield strength will be high because I have to stretch the bonds. Okay, so if bond strength is high, the stretching will be difficult. In case of ionic covalent bonds, okay, the atoms are having, because of this high bond strength, okay, and electrons are shared or exchanged between the two atoms, it has very low conductivity. Okay, electrons are not available for conductivity because it is being shared or exchanged between the two atoms. Behavior is also brittle. Right now you may not know this term, okay, but later on when we will go to mechanical behavior of materials or the mechanical properties, okay, you will understand what do we mean by a brittle property. Okay, but right now you just take it that the behavior, the mechanical behavior, or it fails in a brittle manner. Okay. For example, this type of bonds you will find in ceramics or diamond also. Diamond has covalent bonds. Okay. Metallic bonds, the bond strength is moderate, lower than of course ionic and covalent bonds, and of course depending upon the material you will have different bond strength. Okay, for example, tungsten has very high bond strength, okay, very close to what you will find in ionic or covalent bonds. Okay, so again in this case also the bond strength, the melting point, the strength, hardness increases with atomic number. Okay, so in metal the metallic bonds are of moderate bond strength, but this bond strength increases as a function of atomic number. So lower atomic number material will have lower bond strength, lower melting point, lower strength, and so on. And as you increase the atomic number, the bond strength will increase, okay, melting point will increase, the strength will increase, and hardness will increase. So the strength increases as a function of atomic number, both bond strength and the material strength. Okay, and behavior is in metals or metallic bond is ductile. Again, this term may be not known to you, okay, but when we will go to mechanical properties, you will understand this particular term. Again, van der Waals forces, bond strength is weak. Okay, some values are given here for argon, chlorine. Okay, and in case of hydrogen bonds, okay, again bond strength is not very high. So this is for ammonia and this is for water. What will be the bond strength? Okay, so you can understand that for materials and the properties which you actually see in the bulk material, actually they are dictated at atomic scale. Okay, so atoms, how they are interacting, how each atom is interacting with another atom, what is the bond type, what is the bond strength, ultimately that decides the property of the bulk material. Okay, so you can understand that within as we discussed in the first lecture, that when you see a bulk material you just see, okay, this is the property of the material, but it is dictated at that scale. Okay, from there it goes to the bulk material. Okay, so that is the fascinating part of the whole understanding the atomic structure, that at that atomic scale whatever is happening decides what is going to be in the bulk material. Okay, thank you for today. Up to this, that is what is our lecture. Thank you.